Welcome to Chemistry Lover, and today in this video I am going to discuss about a very important name reaction. The name of the reaction is the Kinugasa reaction, and although it is not mentioned in any of the syllabus of your competitive exams or BSc or MSc, but the reaction is quite simple. You can see the reaction product is quite simple, and it may come to any of your competitive exam anytime, and that's why I am discussing this reaction. And the reason why I am discussing this reaction is because the mechanism of this reaction is very much interesting, right? So the reaction is actually discovered around 1986 or somewhere around that, but its actual mechanism, the original mechanism, is established only recently in 2018, and the work was published in a very reputed journal of American Chemical Society, or JACS. So let me discuss this mechanism with you. So you can see these are the two components. One is alkyne, a terminal alkyne, where you have hydrogen at the terminus, and this is called nitrone. So between the reaction of this terminal alkyne and nitrone, in presence of copper 1 catalyst, you will get this beta lactam. In this case it is a 4-membered beta lactam which is very strained. Now what is the mechanism? So I will discuss the latest mechanism which is discussed in that particular paper. So the reaction has several steps. First, there is a 3+2 cycloaddition, then there is a 3+2 reverse cycloaddition, and finally there is a 2+2 cycloaddition. So you may think that reaction is a little bit complicated, but I will try my best to explain this as simple as possible. So the first step of the reaction, if you consider, you have a terminal alkyne and you have copper 1, and this will remind you the Sonogashira coupling, where the copper acetylide is formed at first. So here also you will first have this copper acetylide, right? So exchange of this hydrogen and this copper 1 will occur between this terminal alkyne. Now what is the next step? So in the next step you will see, so another copper 1 will come. So copper 1, so this copper 1 may be given in the form of copper iodide or copper, other salt of copper chlorate, like that. So this copper 1 will come and it will actually coordinate with this triple bond. So here you will have a coordination with this copper 1 and this triple bond, and this will activate this triple bond. Now what will happen? This component, this nitrone, this will come to this reagent. So you have this copper, and here you have this coordination with this copper, or let me draw it this side. So let's say here you have this coordination with this copper, and now you will see, draw it this side. So now you will see this will come. So this is the nitrone. So you have this pH, this double bond N, and this is your oxygen, right? And here you have another pH. So this is the thing, right? So this oxygen will now bind with copper. This oxygen will bind with copper because it has a negative charge, and we can write it like this. So here we have this copper, here we have this oxygen, and this side we can see, so sorry, this, and this side you can see, so another pH over here and this pH over here. So now this is coordinated with this copper. Now you can see this actually remains as O minus and here you have plus. So this is a 1,3 dipolar species and this is a triple bond. So there will be a click chemistry, you know the click chemistry, a cycloaddition will occur. So this is how the cycloaddition will occur, and what you will get is this pH, and here you have this copper, and this side you have this copper, this side you have this pH, this nitrogen, this oxygen, and here you have another pH. So this intermediate you will get. So this is the intermediate which you will get out of this reaction. Now, so this is the product of cycloaddition, and here you can see the copper was in +1 oxidation state. So actually here oxidative addition is occurring on the copper, and this copper will become +3, right? So oxidative addition is occurring between this copper and these two species. So here you will have +3 oxidation state of the copper, and then if the reductive elimination occurs, what you will get? So you will get here you have this NO, this copper will remain as it is, and here you have this pH and another pH over here, and here you have another pH. So this is the thing which you will get out of the reaction after the reductive elimination, or you can just simply write like this. So if you don't want to confuse yourself, you can simply write this one. So here you have this one, and this side you have this O minus, here this phenyl, another phenyl is over here. So you can just write like this, and this will give you this product. So actually this intermediate is mentioned in the paper, and that's why I am showing it, but for remembering you can think of like this. So this is a 1,3 dipolar species, this is a triple bond, and the 2+3 cycloaddition, this is actually 2+3 cycloaddition between these two components will give you this product, right? Now this product will collapse in a reverse 2+3 cycloaddition pathway, and if the same reverse 2+3 cycloaddition occurs, you will get this actually these two components. But if it breaks in other way like this one, so what will happen? So you will get this pH over here. So this is one component you will get, and the another component is from the upper part, and this is pH. This copper is over here, you have O minus over here and plus over here. So this is the thing you will get. So this is now a 1,3 dipolar species, and this can actually rearrange itself like this. So if now this O minus push back, this will come here and it will become, so here you can see pH, this you have copper over here, and you have this. Now this becomes a carbene, this becomes a carbene species, right? And now if the protonation occurs at here, so you will see, so this is like so in place of copper now you will have hydrogen, so protonation will occur. Here you have H plus. So actually with copper 1 acid catalysis is also used there. So this protonation will occur and this will become now this, and now if this hydrogen is shifted over here, so this will become negative and this will go here. So this is how you will get this ketene. So this ketene species you will get out of here. So from this part you will get this ketene, and from this part you will get this imine. So again let me tell you how this ketene formation occurs. So actually this proton exchange, you can see this proton exchange between this copper and this proton, this can also happen in this step. So after getting this one, maybe the proton exchange occur and you will get this. So this proton is always there, so you may have this, right? So after the formation of this carbene, you can see how the carbene is formed. So here you have plus, here you have minus, and when this minus push here, this bond will go here. So this carbon become a sextate and it is a carbene now. Now this carbene, as it is formed, this hydrogen is actually shifted to this carbene, so then it will become negative, and this negative will push over here. So this is how this carbene is formed. Normally in case of Cartesian rearrangement or any other rearrangement, this is how the ketene is formed. So now we have two components in our hand. One is our ketene and one is our imine, right? So let me now again draw it. So this is the ketene partner and you have this partner, and now here you have this N pH, you have this pH thing. So now you can see 2 plus 2 cycloaddition can occur, and if this 2 plus 2 cycloaddition occurs, what you will get? So you will get this product. So here you have phenyl, so this side, this is below the plane and this is above the plane. Now if I have to explain the stereochemistry, so you can see, so if this phenyl is here and this hydrogen is over here, so if this particular component is approaching from above the plane, so what will happen? This phenyl will go below the plane, this hydrogen will come above the plane, right? And now if the antifacial reaction occurs, because 2 plus 2 reaction in thermal condition is antifacial, so if antifacial reaction occurs, what will happen? This phenyl group will come above the plane and you will get this product. So this is the overall mechanism for this Kinugasa reaction, and you can see this reaction is quite complicated. So I hope that you understand the mechanism, and if you want to read that paper, I will give the link of this paper in the description section. Thank you for watching.